All right. Welcome to today's KCS talk. Okay. The speaker today is Mr. Brennan Graham. He's one of our own. He's a senior student of our department. Okay. The title of his talk is Introduction to MITRE and the federally funded research and development centers. Okay. He will describe the history and the purpose of federally funded research and development centers with a focus on the MITRE Corporation, followed by a reflection on what skills were most useful and what the speaker wishes he had known earlier. Okay. This talk, of course, is very useful for junior faculty members. Unfortunately, none of them are here. Okay. Even though we announced this several times. Okay. MITRE is a government-funded organization which applies systems thinking to solve complex problems and provides objective technical analysis to serve the public interest. Okay, let's welcome Mr. Graham for today. Okay. Remember that if you have questions, please raise your hand and we'll give you the mic.
Sounds good. Well, thank you all for being here today. As you said, my name is Brennan, and I'm a senior here at UK, double majoring in computer science and economics. And I'll be sort of speaking today based on my experience as a software engineering intern since last October with the MITRE Corporation. So just to give you kind of a roadmap of where I'm going to be going today, I'm going to start out with a description of what federally funded research and development centers are in general before going into a bit of the history of the MITRE Corporation in particular, which I think provides a good illustration of the kind and nature of work that these organizations are well suited for, before diving in a bit deeper into some of the current work that MITRE is doing with a particular focus on their work related to defense and security. So FFRDCs, or Federally Funded Research and Development Centers, were originally founded about 70 years ago at the beginning of the Cold War. And they've always been focused on supporting things like government research, technology development, systems acquisition, and policy guidance, and started out specifically focused on work for the Department of Defense, but have now expanded to include a wide variety of subject areas, including transportation and healthcare. It was originally set up in something called the Federal Acquisition Regulation, or FAR, which is basically a large set of federal laws that define how the government spends money and acquires things. And the two sort of key parts of this regulation are that it defines that FFRDCs will have a sort of special relationship with the government, meaning that they can see and access information and provide advice and analysis that a traditional defense contractor cannot. And they're able to do that because they are mandated to operate in the public interest without a profit incentive, which enables them to have a higher degree of objectivity and independence than would otherwise be possible. So this enables these sort of 5 key characteristics of a federally funded R&D center. First off, FFRDCs, as I said earlier, are mandated to work in the public interest. So they're actually not allowed to work on anything that a contractor could be doing. So if it's possible to privatize it in some way or have a for-profit company working on it, FFRDCs are not allowed to touch it. So they're exclusively working on things where you've got this sort of unique perspective that's needed where you can bring in a sort of truly objective third party. Secondarily, as I said, FFRDCs cannot compete in the marketplace, can't go up against a contractor, but they're still intended to advance technology and promote the economic health of the country. So what this basically means is that as they develop technologies, as they work on research, they, whenever possible, are trying to push that out into the broader research community to enable greater understanding in academia and industry, and often something that an FFRDC has worked on will get licensed out to a private corporation so that they can then go sell it or adapt it into some kind of product that would make sense in a private marketplace. Thirdly, because they kind of stand in between the government and the private sector, they can bridge a lot of gaps where they are often trusted with government information that they cannot hand out to contractors because it might improperly influence the bidding process for contracts, but can also receive proprietary information from the private sector companies that they might not be willing to share with the government because they're the ultimate decision-making authority on contract bids and that kind of thing. So because of this, FFRDCs can often have a sort of better big picture understanding of what might be going on in a way that fuses both the policy and technical sides than either the government or the private sector could have alone. Fourthly, FFRDCs are really focused on applied research, so not much that they're doing would fall into the category of sort of pure basic science. It's really focused on mapping areas of technological discovery or need back to problems that the government sponsors are facing. And fifthly, as I've sort of, as has come up in several different ways, FFRDCs are trusted to work independently and without commercial conflicts of interest because ultimately they don't have shareholders, they don't have a profit incentive mechanism, so they're able to be a bit more clear-eyed about what the best solution might be rather than maybe trying to sell a more expensive solution that would bring in more money. So FFRDCs can fit into one of these three basic categories, with the first being study and analysis centers, which are primarily focused on policy and social science research. And on the other end, you have what are called research and development centers, which are much more focused on technical and R&D research. And then in the middle, you've got systems engineering and integration centers, which try to sort of bring those two sides together. So they're not necessarily purely focused on technology or purely focused on policy. They're trying to map policies to technologies and vice versa so that you can achieve whatever goal you're setting out for. So some examples of these kinds of organizations would include, of course, MITRE, which I've been working with, as well as the Aerospace Corporation, and both of those fit into that Systems Engineering and Integration Center model that I was talking about on the previous slide. And then you've also got on here RAND, the Institute for Defense Analyses, and the Center for Naval Analyses, which fall into more of the Study and Analysis Center bucket. And then finally, the logo in the bottom right is for the Lincoln Lab, which is actually based out of MIT and falls more into that sort of R&D technical focus kind of role. There's also a related but distinct kind of organization called the University Affiliated Research Center, or UARC, which is functionally very similar to an FFRDC, but is administered by a specific university rather than being sort of an independent organization, with Lincoln Lab kind of being the exception in the FFRDC bucket. So some examples there are UDRI, Johns Hopkins Applied Physics Lab, and GTRI. So now transitioning to look at MITRE a bit more specifically. As I said, they were founded roughly 70 years ago at the sort of beginning of the Cold War, and now have actually grown to be a bit above 10,000 employees, but are focused on providing this sort of objective, scientifically and technically driven approach to solving problems. MITRE was actually originally founded to work on a program called SAGE, or the Semi-Automatic Ground Environment, which was the first integrated air defense system really in the world. And it was driven by concerns that if the Soviet Union was to launch an air attack on the United States, the US military at that point did not have a way to effectively detect what was coming in and to then figure out how to best dispatch their defensive assets like interceptors or missiles to be able to effectively mitigate that threat. So systems engineering responsibilities for this system were originally originally given to the Lincoln Laboratory at MIT, but because of the spectrum of problems here and the size of this project, which eventually actually grew to exceed the Manhattan Project to build the first nuclear bomb, it was really kind of taking up all of the oxygen at Lincoln Lab. And they wanted to work on other things and didn't want to be exclusively doing air defense for who knows how long. So eventually they decided to sort of spin off MITRE as a separate organization to initially just focus on this project, which, while it touched on a lot of areas, was kind of at its core a computing problem, because you're trying to take in data from all these different sources, process it and fuse it together, and then use that to make a good decision about how to allocate your resources. So as a result of that, one of the key advancements that came out of the SAGE program was the Whirlwind 1 computer, which you can now see part of at the MIT Museum. And it was notable as being the first computer to use magnetic core memory and is considered to be the first sort of real-time computer, which was driven by those computing needs that I was talking about earlier. Because, of course, it doesn't matter if you can figure out the optimal way to deploy your interceptor planes or surface-to-air missiles if you only get the results 24 hours after you threw in the data, because then you're it's kind of done and gone, right? So it could, to meet that need, it was capable of doing a blazing 50,000 add operations per second, and soaked up over 100 kilowatt hours of power, but it was certainly a big step in its day. Another example of a way that MITRE has contributed to the growth of computing and computer science as a field was that they were heavily involved in the design of ARPANET back in the day. As you can see sort of in the red circle there, they had a node on the original ARPANET, and a lot of the system design actually grew out of the work that MITRE was doing on SAGE, because to get all of that data to Whirlwind 1 for processing, you had to engage in some fairly extensive networking to run lines out to all of these different radar sites and out to the Air Force bases where you would be then deploying the fighter assets. So that experience naturally kind of transitioned into the creation of this military network that's the predecessor to what we now know as the internet. And MITRE actually was the first organization to register a .org domain on the internet as well. So it's a sort of long history there. Another piece of work that grew out of that SAGE program is known as the Traffic Collision Avoidance System, or TCAS, which if you've ever flown on a commercial airliner, TCAS was on there. Basically, it is a piece of hardware that goes onto the plane that takes in the sensor data from the plane to determine if there's any other aircraft nearby that is on a collision course with your plane. And then if there is, it will reach out to the TCAS system on the other aircraft to negotiate a resolution to that collision trajectory. So to try to find a way for you not to crash into each other. And the two kind of key issues that you're trying to solve here is that, first of all, the pilot may not notice if he's about to crash into another plane, which would be a problem. And secondarily, even if he does, if you've ever been walking down a hallway and you are walking towards someone and you both step in the same direction and you're still on a collision course, that might be fine in a hallway where you can stop and laugh a little bit and turn. But if you're in the air and you both sort of zig in the same direction, you may wind up crashing into each other still. So TCAS will automatically contact the system on the other plane and negotiate the best way for both of you to move to avoid that collision trajectory. And once again, this grew out of the SAGE work because there was an extensive need for better air traffic control and air traffic management as part of this integrated air defense system so that you could keep track of all of your assets and avoid them crashing into each other. So as kind of a summary, MITRE initially started working on SAGE exclusively, but that grew and evolved to a wide variety of areas that has continued to expand over the past 70 years to a wide variety of domains, now also including things like health and human services and homeland security, which I'll talk about in a bit more detail in a moment. And that work has also expanded from just being sponsored by the Air Force to now including really almost every major federal organization having some kind of relationship with MITRE, including basically every major element of the Department of Defense, as well as a variety of non-defense and security-related organizations, as you can see on the screen here. And that work is managed by 6 federally funded research and development centers that kind of fall under the umbrella of MITRE. The first of these is the Center for Advanced Aviation System Development, or CASD, and this is the one that handles most of that FAA-related work. So TCAS would be included here, as well as more generally, MITRE helps to design the National Air Traffic Control System that fits together all of the FAA's ground tracking radars and the ground traffic management at airports to try to manage the complex web of commercial flights that transit the US each day. They're also currently working to develop the next generation version of this system, which is going to be necessary to be able to truly leverage a lot of emerging technologies such as air taxis, as well as to enable the continued growth in use of drones, and especially autonomous drones, in US airspace, which the system was not really built to anticipate back in the day. Additionally, this work is needed to enable the sort of rise in commercial spaceflight that's currently happening, because back in the day when the system was originally developed, the only people flying in space were NASA, and so you could block off a massive area of airspace every time they were doing a flight and not have to really worry about it, both because there were fewer commercial flights and because they're maybe sending up a handful of things a year. now with SpaceX and Blue Origin and even NASA launching more stuff than they used to, that's simply not a sustainable path forward if you're going to have anywhere near the kind of projected growth in commercial spaceflight that we're expecting. There's also the Center for Enterprise Modernization, which is sponsored by a variety of civilian agencies and is primarily focused on helping them to upgrade and modernize their IT and data processing infrastructure. As anyone that's filed your taxes probably knows, the federal IT systems can be cumbersome and not ideally optimized for the task. And so, yes, that would be a good adjective. We're trying to help them to modernize their systems and leverage what is sort of possible now to offer a better experience to the taxpayers and hopefully to do so more efficiently and effectively. There's then the Health FFRDC, which is primarily sponsored by the Department of Health and Human Services, although they also work a lot with the Center for Medicare and Medicaid Services. And the most exciting project here, at least in my opinion, is the the effort to create a standardized electronic health record for all healthcare providers to use across the US, which would greatly increase patient portability because you'd be able to just take the health information file from your current provider, walk it down the street to your new provider, give it to them, or more realistically have it emailed or whatever, and have all of your data populate in their system in a way that would be standardized and hopefully as close to a seamless experience as possible. This would also open a lot of exciting doors for health informatics because you would have all of this data in a standardized format with common units and common fields, which would dramatically overcome a lot of the data cleaning challenges that are currently faced by researchers that are trying to understand public health trends and that kind of thing. That would be very exciting if it's able to be adopted. There's also the Homeland Security Systems Engineering and Development Institute, also called HISETI, because of course MITRE's government adjacent, so there's an acronym for everything. They do a lot of work with the DHS agencies, including work on border security and trying to stop human trafficking and smuggling and that kind of thing through the application of advanced sensors and other forms of data processing. And they also do a lot of work with FEMA, trying to promote communication and resilient sort of systems engineering design for emergency response. So if all of you got a loud emergency alert on your phone a few weeks ago, you can partially thank MITRE for that because they were serving as one of the technical validators for that test of the integrated public alert and warning system. One of particular note to the computer science department is MITRE's work with the National Cybersecurity FFRDC, which is actually sponsored through NIST. And the primary thing that they're focused on here is to create a common sort of framework of language and definitions for use in describing cyber threats. So this is probably the thing that MITRE is best known for in the popular imagination, but if you've ever heard of something called the Attack Framework or Atlas or Caldera, all of those are sort of open source cyber threat definition frameworks that were created by MITRE and are now used by most of the Fortune 500 as well as the government and a variety of nonprofit and NGO type organizations. MITRE is also responsible for managing the CVE, or Common Vulnerabilities and Exposures database. So if you've ever dug into why you're having to update your computer and saw, oh, this is to address threat CVE-whatever, that designation came out of a MITRE lab. And finally, the organization that I've been working in is the National Security Engineering Center, which is really continuing that legacy of work that started with SAGE. So it has now expanded well beyond air defense to include really any major defense acquisition or technology program. And the key goal here is to help the government to understand the technological challenges that they're facing as they try to achieve whatever policy goal or national security goal, and to help them to find the proper mix and match of technologies and other policies that will enable them to actually achieve that goal well, right? Because if you go to any particular contractor, they're going to tell you that, like, oh, our massive system is the only thing you need to buy to address your issue. And our role is to help the government find sort of the mix among the contractors and among other sources that will actually address the issue most effectively. So all of that fits into this sort of organizational structure where the national security work is lumped together, and then all of the civilian work is put together under the public sector. And there's also an organization called MITRE Labs, which I've not referenced previously, which is organized around areas of technical capability rather than areas of sponsor need. And so this enables MITRE to assemble teams that can effectively address any particular project or problem that a sponsor might need by assembling together the right group of people from MITRE Labs, which are specialized around technical areas. So for example, there might be a department in MITRE Labs that's specialized in software engineering, and another one in data science, another one in operations research, and so on. And then, a department in MITRE Public Sector might be specialized in air traffic control management. And so if you have a software engineering problem in air traffic control management, you can pull together people with expertise in both areas, match them together for the project, and be able to rapidly deliver that expertise to the sponsor. Within the DoD work program in particular, most of the stuff that MITRE is focused on today falls into one of these 5 areas, the first being what they call redefining strategic deterrence, which basically means modernizing the nuclear command and control and communication structure for the United States to adapt it for a world where it's no longer a sort of comparatively simple binary competition between the US and the Soviet Union, but is now in a truly sort of multilateral nuclear environment where nuclear weapons have proliferated to the point that many countries have them and could threaten to use them. So trying to build systems to be resilient and to provide decision makers with as many options as possible so that you can de-escalate more effectively. And there's also some work ongoing to try to prevent the further proliferation of nuclear weapons, particularly their acquisition by criminal or non-state groups. Then MITRE is also working to help with the sort of transition in mindset from national security to international security. And what we sort of specifically mean by this is taking into account ally and partner capabilities when you are buying or acquiring new weapon systems. So, or when you're defining policies and trying to make things more interoperable. So using common communication standards and common data formats is really critical if you're going to be able to effectively communicate in the heat of battle with your allies who might be using very different equipment. And it also can shift what it makes sense to buy if you are considering what your allies are also buying and what they are also capable of, rather than if you just look at it on a sort of nation-by-nation basis. Of course, a critical component to national security is also protecting the US economy, which includes protecting US critical infrastructure like the electrical grid or water supply, as well as promoting US industrial strength. And then there's also growing sort of emphasis on defending our democracy from things like foreign interference in our electoral processes or information operations that are seeking to sway political opinion here in the US, with probably the most publicly notable part of this work being MITRE's Election Security Lab, which is seeking to sort of audit and verify the security of election machines across the United States to help to increase public confidence in the electoral system. And finally, the sort of MITRE systems engineering and systems of systems approach is especially useful when addressing global threats like climate change and pandemic disease, because ultimately for these kinds of grand scale problems, there is no single solution that's going to be a silver bullet. So this sort of comparison across a wide variety of options and fusion of different solutions to reach a large goal that MITRE has been working in and honing since the SAGE days is going to be an important part, I think, of addressing these global challenges. And then within that MITRE national security sector, this falls into either the Air and Space Forces bucket, the Joint Services bucket, or the Intelligence bucket, with Air and Space Forces obviously handling anything related to the Air Force or Space Force, Joint Services kind of taking anything else in the DoD, and then the intelligence folks taking all of the three-letter agencies. And doing all of this work requires a very wide variety of backgrounds. So there's folks that are obviously specialized in computer science, as well as electrical engineering, systems engineering, and a variety of other disciplines. And that enables delivery of work ranging from systems engineering to data analytics, and also sort of objective evaluation and implementation of things that may have been designed by other people but couldn't be brought that last mile apart from MITRE's intervention. And that work is split roughly a third across each of those areas that I mentioned earlier. So some key characteristics that I found as I engaged in this work through the internship was the ability to learn rapidly. So being able to get up to speed quickly on new areas was very important because, as an example, a lot of the work that I was doing was related to radar systems, but as a computer science major, I never took physics 2, so I never actually studied electricity and magnetism in a formal classroom setting. So I needed to get smart on that rapidly to be able to understand what was going on and be able to bring value to the team. As a result of that, I also learned the importance of identifying similarities and analogies across disciplines as a way to sort of speed up that learning process. Being able to find ideas that show up in multiple places makes it easier to do that rapid learning. And finally, as I sort of got up to speed, I also saw the importance of recognizing the assumptions that I was making, because if I'm, say, building a computer model of something, if I don't understand and define well the assumptions that I'm making, then my results could be utterly invalid or could have key limitations that I'm not aware of or acknowledging as I'm presenting them. And then on a more sort of like tangible basis, most of the work that I've done has involved programming in MATLAB and Python, so I've actually wound up using EGR 101 and 102 and 103 a fair bit. And I also have been using source control in Git quite a lot, which is at this point kind of a major factor in almost any major software engineering organization. And so I'm very grateful to get a more formal introduction to it in Dr. Ebby's class now, but it would have been helpful to perhaps get that at a sort of like first-year engineering type level, just because it is so big in industry at this point. And finally, as you may have gotten an impression of on the slides with the pie charts earlier, almost no team at MITRE, and really increasingly a few teams in industry, I think, are going to be only software engineers talking to software engineers. And so I think that really emphasizes the importance of communicating across technical boundaries and being able to avoid using your own jargon and sort of engineering or computer science slang, and speaking clearly and plainly, and being able to understand the jargon or technical terms that others are using if they're either not able to avoid them or just choose not to. So yeah, I think all of these factors are important, and overall I would say that my UK education prepared me well to be able to step into this role and do this sort of exploration. Yeah, so that's all I really have for you. So thank you for your time today. I really appreciate it. And I'm going to try to answer any questions you guys might have.
How large is the internship program? I mean, how many interns? It's okay. Yeah. No.
Yeah. So MITRE has, about 500 interns across the organization.
Wow.
Most of those are at the larger sites in Bedford, Mass, which is where I was, and then there's a large campus in McLean, Virginia, just outside DC. And then there's a handful that are at the smaller sites. There's about 30 of those smaller sites around the country, but mostly clustered near military bases. But, so it's a big program. But, and applications are also live now if you have any students that would be interested.
So, wow, was GitHub something you used at MITRE, or is that, do they have their own GitHub thing? It's a little bit surprising to me that they would put stuff out.
Yeah, so they have a instance of GitLab that they use. So it's internally hosted, but still uses the Git framework. So it's, certainly not being posted on like third-party servers with GitHub. But although some of the, so they occasionally develop like threat models that they'll like send out to industry and that kind of thing. And so in that case, it'll often go on GitHub as a way for them to access it easily. But Git in general as a basis for source control seems to be kind of the universal standard at this point.
Thanks. Now I forgot what I was going to ask. Let's see. Well, I don't remember. Sorry. Went out the door.
Okay. Anyone else? Apparently this is very sensitive.
To whatever extent you could go into it,
Yeah.
What were your responsibilities like? What is, I think there's this idea that there's almost a dichotomy between being a student and then actually stepping into industry and like having responsibilities and working on a team on projects. And so what was that transition like for you at MITRE?
Yeah, so I think that transition was helped some by the fact that I'd done previous internships. So it wasn't my first time working in a kind of corporate type environment. But my particular responsibilities were helping to develop computer modeling and simulation tools, mostly for radar systems. And I was fortunate to be stepping into a team that gave me real work, because I think there's often there can be kind of a varied experience with internships where you might be handed kind of toy problems or things the company doesn't really care about because you're an intern and you're still learning. But I was very lucky at MITRE to be given work that was significant to them and the work that mattered, although they were certainly by my side helping me to do it and making sure that I was delivering high quality code and analysis based on the code. And I guess the particular thing that I really liked about the work that I was doing, and that was kind of different from my academic experience, is that it was open-ended in the sense that I really had to like define the problem that I was solving in addition to then going on and solving it. Whereas in the academic world, or at least as a student, you are given you're given the problem definition up front and then just asked to solve from there. So it was cool to have the freedom to be a little more creative and to think through what I was doing in a little bit more detail. And I also enjoyed the sort of interdisciplinary aspects of the work at MITRE, where I wasn't just doing software engineering, but was also learning about the electrical engineering or the like military policy stuff that fed into the problem we were trying to solve. So that cross-disciplinary aspect was very cool, and I think there's an increasing focus on that in academia, but it was neat to see an organization that may be further along in that development.
So I remembered what I wanted to say, which was thank you for going through the not trivial process of getting all of this approved, right? I know you had to get permission to say all these things and show the slides and everything, so thanks for going through that, which is one of the maybe downsides of that kind of position, right?
Yeah.
The other thing I wanted to ask as a kind of follow-up was the people that you were working with, were they sort of all sort of PhD types or long-time industry types or what?
Yeah, so the main team that I was with was relatively young. I mean, they'd all probably been there for maybe 5 to 10 or 12 years, at least the folks I was working with on a day-to-day basis. So there were a couple of them had PhDs, but most of them were either bachelor's or master's graduates that had then kind of gone into industry.
So you mentioned 500 interns. How many of those are computer science students?
Actually, I don't think I have that on another slide.
Roughly.
I would say maybe a third to a half.
That's significant.
It's a large chunk. I mean, the other biggest chunk would probably be aerospace engineers. And I mean, I'm also lumping in like people that might be like software engineering majors or like a cybersecurity major or that kind of thing.
Right.
But
how did you get connected with them?
yeah, so I actually learned about MITRE through a economic data analysis competition hosted here at UK called the Econ Games, which brought in the guy that's now my boss as a sort of guest speaker to talk about some of the work they were doing with air traffic control modernization. And I found his talk super interesting and followed up afterwards, and that led to the job. So got very lucky there, but they, well, sure, but very, very fortunate, I should, is maybe a better word, but. Yeah.
All those, like MIT and everything else, there was a
Well-
mention of the University of Dayton. Was that right?
That's correct, yeah.
Yeah. What, did you run into any University of Dayton people?
Yeah, I have actually. Well, actually, I was in the Dayton office on Monday, working a little bit. So there were certainly have some Dayton folks there, but the University of Dayton has a very strong relationship with the Air Force as a result of their proximity to Wright-Pat.
Well, excuse me, I have two questions for you. I don't know if the first question is appropriate.
Okay.
But the number of employees of this MITRE place is 9,000 something.
Yeah.
Do they really need that many people?
For the amount of work that MITRE is being asked to do, I think so, yeah. It's grown a lot over the past few years, but we always seem to have more stuff that the government wants us to do than we have people to do it. So I would call that a good sign, I guess.
Okay, my second question is that,
Please take 3 steps forward.
oh, all right. So this is a better place, location?
Yeah.
All right, the second question is that I don't think it's, for those areas that they would, like to search, research, proposals. I think it's probably more appropriate for computer science people to work with somebody, like in the space engineering, or mechanical engineering, or security, system. So do they prefer that a proposal directly sent from the computer science department, or joint proposal with, like I said, space engineering?
So I guess to clarify slightly, there's not really a mechanism for academic researchers to directly submit requests for funding or that kind of thing to MITRE. I'm not sure if that's what you were getting at exactly, but certainly there is a strong preference for interdisciplinary work and interdisciplinary approaches, because very few of the problems that our sponsors are facing are pure computer science problems, right? Like it's almost always computer science as applied to military operations, or computer science as applied to this electrical engineering problem. So it is certainly important not to work in a vacuum. So being able to work and talk well with people from those other backgrounds and other disciplines is critical. And you also, even if it is a pure computer science problem, need to be able to communicate why it matters and what it is and why it's significant to people who have no understanding of the field. Because often the people that are ultimately in charge are military officers or civilian officials that have no reason that they should be experts in computer science. And so you need to be able to explain that value add to them well. I'm not sure if that answered your question exactly.
Well, sort of, yes.
Okay.
Thank you very much. Any other questions? We still have a few minutes to answer questions.
Do you have any tips or advice for somebody that's not even just necessarily interested in MITRE, but interested in kind of FFRDCs and the intersection between federal research and industry?
Yeah, definitely. For any kind of work in this space, I would say that it's helpful to have some kind of prior research experience. So being able to get involved with that on campus here or through some sort of exchange program with the university might be a useful sort of step in that direction. And also because a lot of this work winds up being having significant security ramifications, getting a security clearance is a significant part of being able to work at a place like MITRE or other FFRDCs, although not all of the work requires it, but a high percentage does. So if you can do an internship that would get you that clearance, then that would be helpful. And more generally, being able to show that you can learn quickly, especially in an interdisciplinary context, is important. So I think it probably helped me that I was doing a double major. But even if you're getting involved with other clubs and student organizations where you're working with cross-functional teams, I think that would be strong experience to highlight in an application.
All right, we thank you very much.